What's up, guys? This is Jahangir from Edporium, and today we're going to be talking about the differences between ionic versus covalent bonds. So let's start off by talking about ionic bonds, and these are going to be opposite charged ions. So the bond is going to be between two or a couple of oppositely charged ions. So the bond is going to be between oppositely charged ions. And when we're talking about these oppositely charged ions, we first off have those positively charged ions, which are known as our cations. And we also have our negatively charged ions, which are known as our anions. So ionic bonds are usually between metals and nonmetals. For example, if we had something like NaCl. So we have sodium, NaCl. So the sodium over here, sodium is going to act as a cation. Now, what cations do and what makes them positive is that they donate their electron. So what happens is the sodium will become positive because it donated its electron, versus when we have that chlorine over here, and we just have the G is in our gaseous state. So actually, let me put that over here as well with our sodium right here. So our chlorine is going to accept an electron. That's what makes chlorine negative. So let me write over here. It is that cations, what they do is they donate their electron, and anions, what they do is they accept electrons, and this is what creates their bond. Now, the reason why cations donate their electron and anions donate their electron, and we'll talk about sodium real quick to illustrate this, it is that, let's say this is our Bohr's model diagram of a sodium. Let me actually change the color real quick. So this is our Bohr's diagram of sodium. So this is sodium over here, and sodium is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons, while chlorine is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17 electrons. So chlorine is going to have 17 electrons. Now over here, that sodium, and if I zoom in real quick and just focus over here. So this sodium has 1 electron on its outermost valence shell, while this chlorine doesn't really have that. It needs 1 more electron to fill in that octet rule. So let's actually talk about the octet rule real quick. So let me actually change my font. So the octet rule is basically this idea of filling 8 electrons in these outermost shells, which over here is just 2. So the most innermost shell, we need to fit 2 electrons. Rest of them, we need to fill in 8. So to fulfill that octet rule, now the sodium can just give up its electron easily, because this chlorine is really needing 1 more electron in order to fill in that octet rule. Because when we fill in that octet rule, we have a more stable atom. We have a more stable element. So what happens is this electron will transfer over to chlorine, and that's when the ionic bond is created, because we can lose this electron from sodium much easily than we can lose it from chlorine. So the sodium will donate its electrons for chlorine to fulfill that octet rule, and we have an ionic bond. So this is what we see with cations and anions. Anions want to fill in that valence shell, that outermost valence shell, and they want to fulfill that octet rule, while cations are more than willing to give away their electrons so that octet rule can be fulfilled. Now, in order for this electron to basically break apart from this valence shell over here, we need something that is known as ionization energy. Ionization energy. And this is the energy required to basically remove that electron. If we have a high ionization energy, it's going to be difficult to remove that electron or to lose that electron, because with that energy, we just need so much effort in order to pull out that electron. But if we have a low ionization energy, which is what sodium has a low ionization energy, it's much easier for that chlorine to pull that electron away, and that's what ionization energy pretty much is. It is because usually with cations, they're going to have a pretty low ionization energy, while our anions are going to have high ionization energy. So it makes sense for our cations to donate an electron to our anions. Now, a couple of key concepts to know is when energy is absorbed, or energy is absorbed when bonds are broken. When bonds are broken. And this is known as an endothermic process. Endothermic process is endothermic just means absorbing energy. So when energy absorbs, so energy is absorbed when bonds are broken. And the way that I like to memorize this is think about a divorce. With a divorce, there's so much effort and there's so much paperwork and so much time, even money, put into breaking a marriage. So that's what I think about when I think about energy is absorbed when bonds are broken. Because with a divorce, it's really hard and it takes a lot of effort to break that bond. Now, the opposite of that is energy is released when bonds are formed. And this is also known as an exothermic process. So this is exothermic. So energy is released when bonds are formed. So what's the opposite of a divorce? An opposite of a divorce is a marriage. And if you think about it, with a marriage, a bond is created and energy is released by a celebration where you have cake, you have dancing, you have just a wedding. So when I think about energy being released when bonds are formed, I think of a marriage because bonds are being formed and it's a celebration through a wedding. While divorce, that bond is trying to be broken and there's a lot of energy that needs to be put in to file the paperwork, money, and just a whole mess. So that's how I memorize the energy being absorbed when bonds are broken and energy is released when bonds are formed. So hopefully that helps you guys in terms of memorization and understanding this. Now, with ionic bonds, you have to understand that these are mostly in inorganic compounds. And since we're in the topic of organic chemistry, that's when we really dive into covalent bonds. And covalent bonds are the bonds that we're mostly going to see with these organic compounds. So, what is a covalent bond? So, what is a covalent bond? A covalent bond is when we share electrons, whereas with the ionic bond it was an oppositely charged ions that made the bond. With covalent bonds, we're having a sharing of electrons. Usually it's going to be a sharing of two electrons. So for example, if we look at H2, so if we look at something like hydrogen in maybe its gaseous form, something like that, we would draw what are called Lewis structures, and this helps us illustrate bonds due to these valence electrons. So we're going to have a hydrogen and a hydrogen over here, and we know that hydrogens have one valence electron. Since they have one valence electron, we're going to be creating a bond, and that straight line just represents two electrons being bonded together, and this is what we see in hydrogen through what we call our Lewis structure. Through our Lewis structure, we can understand that with covalent bonds, we're using these valence electrons and we're basically sharing them, creating that bond. Now remember, Lewis structure only involves valence electrons. And if we're looking at something like for example, fluorine, although fluorine has more than 7 electrons, we're only looking at the valence electrons. And with the valence electrons, fluorine has 7 valence electrons. So we write, and these dots represent our electrons. So 1, 2, 3, 4, 5, 6, 7. And if we wanted to write F2 in our Lewis structure, just fluorine in its elemental form, then we're going to have something like this, F, and this creates a bond, and that is our Lewis structure. Now, throughout these Lewis structures, we have to keep in mind the octet rule. The octet rule. The only way we can create these Lewis structures is if we agree with the octet rule, but there are some exceptions like sulfur and other atoms that don't really need to fill in that octet rule. But with these general atoms, generally we want to fulfill that octet rule. So for example, with this fluorine, although there's 7 valence electrons, each fluorine is going to have 8 electrons, 8 valence electrons filling that octet rule, because as we can see, there's 1, 2, 3, 4, 5, 6, 7 valence electrons, but in total, since they're sharing that electron, we have 8. So this is 1, 2, 3, 4, 5, 6, 7, 8, and this qualifies for that other fluorine as well. So now let's go through some practice, and I want you guys to pause this video and see if you can draw out each of these Lewis structures. Alright, so if we're going to start with ammonia, we first need to put nitrogen sort of in the middle, because with some of these atoms, the least polar ones are going to be in the middle, except for hydrogen. So it's just a note that if you have just one element in there, you usually put in the middle. So nitrogen, we have 1, 2, 3, 4, 5. So we have 5 valence electrons. And this hydrogen over here, we have 1, we have 1, we have 1. So each of these make a bond, each of these make a bond, and each of these make a bond. And that is where we have our Lewis structure. And just to double check, we have 1, 2, 3, 4, 5. We have 5 valence electrons, and we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons to fulfill that octet rule for the nitrogen, and we're also fulfilling the octet rule for the hydrogen because it only has that 1 valence shell, so it's only have 2 electrons to fulfill that octet rule. Now, let's look at methane over here. So methane, our carbon is going to be middle. We have 1, 2, 3, 4 valence electrons. Then we have 1 hydrogen over here, 1 hydrogen over here, another hydrogen, and 1 more hydrogen. So we're going to make a bond there. We're making a bond here, a bond here, and a bond there. And this is what our Lewis structure is going to look like. Just to double check, we have 1, 2, 3, 4 valence electrons, and we have 1, 2, 3, 4, 5, 6, 7, 8 to fill that octet rule for carbon. Now let's look at these other molecules over here. So we have C2H5F. Now usually when we're looking at these molecules, that F over here, we're just going to interpret that as putting it towards the back. So what I mean by this is that we have 2 carbons, but we're putting that fluorine to the farthest end. And automatically, I already wrote the lines, so you could just do that. And this would be H, 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 hydrogen, hydrogen. So we have 5 hydrogens, 2 carbons, and all we have to do is fill in what are called lone pairs, those electrons, and that is our Lewis structure for C2H5F. So you could automatically, like I did, I just wrote those straight lines because subconsciously I knew that there would be electrons there and a bond there. So now let's look at this one, C2H2, and this one may have tripped some of you guys. So if we write down our valence electrons real quick, we have our hydrogen right here. That makes a bond. That makes a bond. We have a bond over here. But then we have 1, 2, 3, 4 of those electrons. So what we could do is we can create what is known as a triple bond. So when we do that, we pretty much eliminate those 4 electrons because like we said, each of these like straight lines just represent 2 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we fulfill both of those octet rules for the carbon since there's 8 electrons, and we have 1, 2, 3, 4 valence electrons. So hopefully you guys understand Lewis structures in terms of filling that octet rule and just drawing them out. And as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.